Quadratic reciprocity law. The statement of this law is as follows. Let P and Q be two odd primes. Then Legendre symbol Q by P is equal to minus 1 raised to P minus 1 into Q minus 1 by 4 into Legendre symbol P by Q. So, this will be equal to minus of P by Q. Minus of Legendre symbol P by Q if P and Q are congruent to 3 modulo 4 and is equal to Legendre symbol P by Q itself. Otherwise, for the proof, we first choose an integer, say f, and we let f be a power of p such that p raised to f is congruent to 1 modulo q. F can be any integer, it satisfies this congruence relation. Such an f surely exists, since we can see that p raised to the integer q minus 1 is congruent to 1 modulo q, as the GCD of p and q is equal to 1 using Little's theorem. So, such an integer f does exist. We can choose f to be any integer which satisfies this relation p raised to f congruent to 1 modulo q. Now, this relation p raised to f congruent to 1 modulo q implies that q divides the difference p raised to f minus 1. We can compare this divisibility relation to a relation which we have seen already, it is n divides q minus 1. When n divides q minus 1, we proved that there does exist a primitive nth root of unity in the field fq star. So, here we have q divides p raised to f minus 1. So, we can conclude that the field f p raised to f contains a primitive qth root of unity, say theta. Now, let us consider the sum g equal to summation over j varying from 0 to q minus 1, Legendre symbol j by q into theta raised to j. Since this is a finite sum involving the root of unity theta, we can say that this is a Gauss sum. Here we will prove that g square is equal to minus 1 raised to q minus 1 by 2 into q. Then we can say that g square will be not equal to 0. Using this result, we obtain g raised to p, which can also be expressed as g square raised to p minus 1 by 2. Product will be g raised to p minus 1 into g will give us g raised to p. So, this is equal to minus 1 raised to q minus 1 by 2. This quantity raised to p minus 1 by 2 will be p minus 1 into q minus 1 by 4 into q raised to p minus 1 by 2. P minus 1 by 2 into this g, and that can be expressed as minus 1 raised to p minus 1 into q minus 1 by 4 into this quantity q raised to p minus 1 by 2 can be expressed as the Legendre symbol q by p. Since we know that a raised to p minus 1 by 2 is congruent to Legendre symbol a by p modulo p. Applying this, we can write q raised to p minus 1 by 2 as Legendre symbol q by p into g. Let this be labeled as equation 1. On the other hand, using definition of G, the fact that a plus b whole raised to p is equal to a raised to p plus b raised to p in the field f p raised to f, and the observation that Legendre symbol j by q raised to p is equal to Legendre symbol j by q itself. We can observe this relation when j by q is equal to 0 or minus 1 or plus 1. Since 0 raised to p will be equal to 0 itself, similarly 1 raised to p will be equal to 1, minus 1 raised to p will be equal to minus 1 itself since p is odd. Applying these results, we can calculate g raised to p in another way also. We have g raised to p is equal to value of g is the summation over j varying from 0 to q minus 1, j by q Legendre symbol j by q into theta raised to j. This whole raised to p will give us g raised to p. And since a plus b whole raised to p, that is the pth power of sum is equal to sum of pth powers, we can express this sum as summation j varying from 0 to q minus 1, j by q raised to p into theta raised to jp. And here we can substitute for this j by q raised to p the Legendre symbol j by q itself, using the observation we made earlier that Legendre symbol j by q raised to p is equal to Legendre symbol j by q itself into theta raised to jp. Now this can also be expressed as summation j varying from 0 to q minus 1 Legendre symbol jp by q into p by q into theta raised to jp. Since we know that jp by q into p by q will be equal to Legendre symbol j by q into Legendre symbol p by q into Legendre symbol p by q, that is Legendre symbol p by q square, and this square will be equal to 1. Even if Legendre symbol p by q is either plus or minus 1, the square will always be equal to plus 1. Since p and q are distinct primes, Legendre symbol p by q won't be 0. Hence we have this is equal to Legendre symbol j by q itself. So we can replace this Legendre symbol j by q by the product of these two Legendre symbols as we have done in this step. So g raised to p is equal to, here in this sum we can bring this Legendre symbol p by q outside this summation, since Legendre symbol p by q is independent of j. So we can write Legendre symbol p by q into summation j varying from 0 to q minus 1 Legendre symbol jp by q into theta raised to jp. Here the variable of summation j does not occur alone. Here j and p always comes together. So we can replace this jp using another variable, say j dash. Then the sum becomes Legendre symbol p by q into summation j dash by q into theta raised to j dash, and here since j varies from 0 to q minus 1, j dash which is equal to jp will vary from 0, p, 2p, etc. q minus 1 into p. But we know that the two sets are complete set of residues modulo Q. So each of these numbers in the first set will be congruent to a unique element in the second set and vice versa. So instead of saying that J dash varies from 0 to Q minus 1 into P, we can also assume that J dash varies from 0 to Q minus 1, since these two sets are the same when considered modulo Q. So we can write G raised to P as Legendre symbol P by Q into summation over J dash varying from 0 to Q minus 1 J dash by Q into theta raised to J dash. When we compare this sum with the definition of G, we can see that this sum is in fact equal to G itself. So we can write Legendre symbol P by Q into G. So we have obtained that G raised to P is also equal to Legendre symbol P by Q into G. From equations 1 and 2, we have minus 1 raised to P minus 1 into Q minus 1 by 4 into Legendre symbol Q by P into G is equal to Legendre symbol P by Q into G. Here we can divide the two sides of this equation by G, since G is non-zero. Then we get minus 1 raised to P minus 1 into Q minus 1 by 4 into Q by P is equal to P by Q. Or we can express that Legendre symbol Q by P is equal to minus 1 raised to P minus 1 into Q minus 1 by 4 into Legendre symbol P by. Thus, we obtain quadratic reciprocity law. Now, it remains to show the proof the following lemma. The lemma states that G square is equal to minus 1 raised to Q minus 1 by 2 into Q. Proof, we know that G square can be expressed as G into G, and it can be written as summation J varying from 0 to Q minus 1 J by Q into theta raised to J into summation K varying from 0 to Q minus 1 K by Q into theta raised to K. Here we can observe that the term corresponding to J equal to 0 in the first sum will be Legendre symbol 0 by Q into theta raised to 0, which will be equal to 0 itself. Similarly, K equal to 0 corresponds to the term 0 in this sum also. So we may consider the variation from 1 to Q minus 1 only in these sums. Now put K dash equal to minus K. Then summation over K dash varying from minus 1 to minus of Q minus 1. But we know that the set 0, minus 1, etc. minus of Q minus 1 and the set 0, 1, etc. Q minus 1 can be considered equal when we consider them modulo Q. So we can assume that K dash also varies from 1 to Q minus 1, and instead of K we will be writing minus K. So the new term would be minus K dash by Q into theta raised to minus K dash. For convenience, we may also replace this K dash by K itself. Here, from the Legendre symbol minus K by Q, we can split this as minus 1 by Q into K by Q. So, and we can take this Legendre symbol minus 1 by Q outside the summation, since it is independent of both J and K. So we have Legendre symbol minus 1 by Q into summation over j and k varying from 1 to q minus 1. And now we can combine these Legendre symbols j by q and this k by q to get Legendre symbol jk by q into theta raised to j into theta raised to minus k can be expressed as theta raised to j minus k. Thus, we have obtained that g square is equal to Legendre symbol minus 1 by q into summation over j and k varying from 1 to q minus 1 Legendre symbol jk by q into theta raised to j minus k. Now, by changing the variable k to kj, we will get g square equal to Legendre symbol minus 1 by q into summation over j and k varying from 1 to q minus 1. Since we know that the set 0, 1, 2, etc. q minus 1 and set 0, j, 2j, etc. q minus 1 into j are two congruent sets. We can assume that after this variation also k varies from 1 to q minus 1 in this summation. And now by changing k to kj, we will be getting terms j into kj, that is j square k by q into theta raised to j minus kj. We can take this j outside and we will get theta raised to j into 1 minus k. We know that Legendre symbol minus 1 by q is congruent to minus 1 raised to q minus 1 by 2 into summation j varying from 1 to q minus 1, summation k varying from 1 to q minus 1, Legendre symbol k by q. Since Legendre symbol j square k by q was in fact j by q square into k by q, and this will be plus 1 even if Legendre symbol j by q is either plus 1 or minus 1, and the product will be equal to Legendre symbol k by q itself. So we have replaced this j square k by q by Legendre symbol k by q into theta raised to j into 1 minus k. So this is equal to minus 1 raised to q minus 1 by 2 into summation over k varying from 1 to q minus 1, Legendre symbol k by q, which is taken outside the summation of j since this factor is independent of j, into summation over j varying from 1 to q minus 1 theta raised to j into 1 minus k. Let this equation be labeled as equation 3. Here we are going to consider a sum related to this sum. Let us consider summation over k, Legendre symbol k by q into summation over j varying from 0 to q minus 1 theta raised to j into 1 minus k. The term corresponding to j equal to 0 will be theta raised to 0 into 1 minus k, that is theta raised to 0, which is 1, plus summation j varying from 1 to q minus 1 theta raised to j into 1 minus k. This is equal to summation over k, Legendre symbol k by q into 1 plus summation over k, Legendre symbol k by q into summation over j varying from 1 to q minus 1 theta raised to j into 1 minus k. The first sum will be 0 since we know that in the set 1 to etc. q minus 1, there are q minus 1 by 2 quadratic residues and q minus 1 by 2 quadratic non-residues. That is q minus 1 by 2 squares and q minus 1 by 2 non-squares. And so when we evaluate summation over k, Legendre symbol k by q, where k varies from 1 to q minus 1, since we need not consider the term corresponding to k equal to 0. In this sum, there will be q minus 1 by 2 plus 1s, since there are q minus 1 by 2 residues. Similarly, there will be q minus 1 by 2 minus 1s also, corresponding to these q minus 1 by 2 non-residues. Hence, the sum will be equal to 0. So, we can substitute 0 for the first sum in the above equation. Plus, the second sum is in fact the sum on the RHS of equation 3. Therefore, from equation 3, we can write g square is equal to minus 1 raised to q minus 1 by 2 into summation k varying from 1 to q minus 1, Legendre symbol k by q, into summation over j varying from 0 to q minus 1. We can write the variation from 0 to q minus 1 instead of the variation from 1 to q minus 1 as in equation 3. Here we can change the variation of j from 0 to q minus 1. Here we can write the variation is from 0 to q minus 1, zeta raised to j into 1 minus k. Let this be labeled as equation number 4. Here we will now consider this inner sum, summation over j varying from 0 to q minus 1, zeta raised to j into 1 minus k. Here the inner sum is in fact equal to zeta raised to 0 plus zeta raised to 1 minus k plus zeta raised to 2 into 1 minus k and so on, zeta raised to q minus 1 into 1 minus k. That is, this is in fact sum of distinct powers of the non-trivial root, zeta raised to 1 minus k. But we know that sum of distinct powers of a non-trivial root, zeta dash, is equal to 0 in fact, since zeta dash into the sum is equal to zeta dash into 1 plus zeta dash plus zeta dash square plus etc. zeta dash raised to q minus 1, and that will be equal to zeta dash plus zeta dash square plus zeta dash cube plus etc. zeta dash raised to q minus 1 into zeta dash will be zeta dash raised to q, and that will be equal to 1 itself. So this is nothing but our sum of distinct powers, sum of all distinct powers of this non-trivial root zeta dash. That is our S itself. So we have obtained that zeta dash into S is equal to S itself, which implies that zeta dash minus 1 into S is equal to 0. But we know that zeta dash is a non-trivial root. So zeta dash minus 1 cannot be equal to 0. Therefore, the only possibility is that S is equal to 0. That is, we have obtained that if zeta dash is any non-trivial root of unity, then the sum of distinct powers of zeta dash will be equal to 0. Therefore, we obtain that this inner sum is in fact equal to 0 itself. So we can see that in the equation 4, this inner sum will be equal to 0 when theta raised to 1 minus k is a non-trivial root. That is, when k is not equal to 1. Since we know that when k is equal to 1, this theta raised to 1 minus k will become theta raised to 0, which is equal to 1, and we know that 1 is a trivial root. So, this theta raised to 1 minus k will give us a non-trivial root only when k is not equal to 1. So, whenever k is not equal to 1, this inner sum will be equal to 0. But here we know that k varies from 1 to q minus 1. So, when k varies from 2, 3, etc. up to q minus 1, corresponding to all these values of k, this inner sum will be equal to 0. Hence, g square can be expressed as minus 1 raised to q minus 1 by 2 into the term corresponding to k equal to 1. And that would be Legendre symbol 1 by q into summation j varying from 0 to q minus 1 theta raised to j into 1 minus 1, that is theta raised to 0, and this is equal to minus 1 raised to q minus 1 by 2 into Legendre symbol 1 by q is equal to 1 itself, and this sum is in fact summation j varying from 0 to q minus 1, 1, that is we need to add 1 q times. Since the variation of j is from 0 to q minus 1, there are q values of j. So, we need to add this q times. So, the sum will be equal to q. Thus, we have obtained that g square is equal to minus 1 raised to q minus 1 by 2 into q, as we have claimed earlier. This completes the proof of our lemma and hence also the proof of the quadratic reciprocity law. Now let us consider an example. Determine whether the number 7411 is a residue modulo the prime 9283. Since these two numbers 7411 and 9283 are primes, and we can observe that 7411 when considered modulo 4, that is when we divide this number 7411 by 4, we will get a remainder 3. And similarly, for the number 9283, when we reduce it modulo 4, we will get the same residue 3. So, by quadratic reciprocity law, since instead of p and q, here 7411 and 9283 are the primes here, and we have seen that p is congruent to 3 modulo 4 and q is also congruent to 3 modulo 4. Therefore, Legendre symbol of 7411 modulo 9283 will be equal to minus of 9283 by 7411. Since this symbol is evaluated modulo 7411, and since this number 9283 is greater than this modulus, we can reduce this number modulo 7411. That is, we can divide this number by 7411 and obtain the remainder. That will be 1872. And here 1872 is a composite number, since we can easily observe that this is even. So, we can factorize this 1872 and we will obtain its prime factorization as 2 raised to 4 into 3 square into 30 upon 7411. When we apply the properties of Legendre symbol here, we will be obtaining Legendre symbol 2 by 7411 raised to 4 into Legendre symbol 3 by 7411 raised to 2 into Legendre symbol 13 by 7411. And we know that even if this Legendre symbol is equal to plus or minus 1, its fourth power will be equal to plus 1 itself. Similarly, 3 by 7411, if it is either plus 1 or minus 1, its square will be plus 1 always. So, we will be getting the Legendre symbol as minus of 13 by 7411. That is equal to minus 7411 by 13. Since when we apply quadratic reciprocity law here, since 13 is congruent to 1 modulo 4, we will get the result Legendre symbol 13 by 7411 is equal to 7411 by 13 itself. That is P by Q is equal to Q by P for these two primes. Now we can reduce 7411 modulo 13. Then we will be getting remainder 1. So we can express it as minus Legendre symbol 1 by 13, and that is equal to minus of Legendre symbol 1 by 13 is 1 itself. So we have minus 1 as the residue of 7411 modulo 9283. This implies that this 7411 is a quadratic non-residue modulo. Thus we have obtained that 7411 is a quadratic non-residue modulo the prime 9283 using quadratic reciprocity law and some properties of Legendre symbol.